Okay, here we go. We're going to make a nuclear reactor. You're going to have to draw some stuff, and you're going to label the diagram. You should get some space ready. You might want a picture of this, but I think that the easiest part will still be, the easiest way will still be for you to draw something. And before we get to drawing, I need to come up with a concept for you based on our warm-up today called a heat exchanger. Remember that if you take a container of cold water into a steamy sauna, imagine that container is sealed. This is open, but imagine it was a sealed container. Okay. When you take a sealed container into a hot sauna, a couple things are going to happen. Maybe you realize them. One thing that's going to happen is you're going to take away heat from the sauna, right? Because you're going to warm up your cold water. So when you walk out of the sauna after 40 minutes, some of the heat of the space will go with your liquid, right? Because you brought in cold liquid that leaves hot, heat has left. We've exchanged heat. Something else is going to happen too, because when you have hot steam and that hot steam gives away its heat, well, that steam is going to cool down to liquid. So you'll probably have a whole bunch of droplets of condensed water. I just got to assume that that makes sense. Cold can in a steamy place becomes a hot can with water droplets on it. I want to remind you that there was not a direct mixing of liquids. So the stuff in the can stayed in the can. We didn't mix them. We just used the metal of the can to transfer temperatures. I wish I had a can, sorry. I didn't remember that part. This is my water glass. But I hope you understand the heat exchange part. Okay. Tomorrow we're going to come back and we're going to break nuclear reactors. But for today, you just got to know how they work. And the key concept is there's like basically 3 cycles. There's 3 parts. One part makes heat using the nuclear reaction. Another part takes that heat to make steam for the electricity. And then the third part takes that heat and dumps it to the environment. So we're going to trace heat leaving the reactor, cold coming into the reactor, and along the way, that hot and cold switching is going to make some steam for us. Okay, that's your key concept. And I'll help you. We're going to break this down. Don't worry. You got to know this whole thing. And honestly, I think that in this case, you probably want to photograph this or screenshot this. And I guess you should probably just cram or memorize the parts, because a whole bunch of these are in your vocab. I'm sorry, I didn't underline them all. I'm sorry, I'm seeing that now. Anyway, there are 3 cycles happening here. And I know it looks confusing. We got time. I'll break it down. You can do this, and you have to do this because it's on the AP test. So watch. Here's one cycle. Watch my, you can see the highlighter, right? Can I make that bigger? No, I can't make it bigger. Sorry. You can see my red dot though. Okay. Here comes coolant across the reactor core. So now it's hot, giving its heat away in this heat exchange. So now it comes in cold, hits the core, goes out hot. Okay. That's one cycle. Here's the next one. Stuff that comes in cold takes the heat from this first cycle. You allow that to expand into steam, like a tea kettle, comes shooting out of steam, spins the turbine, and all that steam gives away its heat, so it condenses back to water, gets heated into steam, gets cooled into water. Okay, that's the second cycle. It goes from water to steam to water to steam. And that water to steam you should realize that's electricity, right? Because that water, if you make it into steam, can spin the turbine, which rotates the magnets past the wires to go make electricity. That's just a plain old generator like we've talked about already. And in order to do that trick, you got to bring in some cool water from the environment somewhere. This could be a lake, a river, this could be the ocean. You bring in cold water from the environment, and that leaves heated. Those are the cold cans in your sauna. Got it? Cold water from the environment makes cold pipes. Those cool down the steam and condense that steam back into liquid. Now you've got hot water in pipes. So you can either spray those in a cooling tower or you can dump those into the ocean. There's two possibilities here. I'll show you those later. So let's look at cycle 1, cycle 2, and cycle 3. Here's our primary cycle. This is also known as the radioactive cycle or the fuel cycle, and you got to know that. Different reactors use a different coolant. It's something that will run over the fuel rods. So remember that the coolant is now radioactive, right? It's been in contact with decaying atoms. So that means that coolant has extra atomic parts. That means it's radioactive too, right? Unstable extra parts. So that coolant is just there to take away the heat. You know, every time that you're splitting an atom, heat is being generated. So you got to dump that heat or you melt down. So that coolant takes away the heat. And remember, we had two problems, right? That's one. The coolant takes away heat. You got to know that. That solves the meltdown problem. As long as the coolant is flowing fast enough, you can get rid of the heat before the core melts. You should keep in mind that that's about 800 or 900 degrees. So that would evaporate. It's kept under pressure so that it can't go to steam. It's like a pressure cooker, or imagine your tea kettle and you're just holding the steam inside. That takes a lot of work, but you probably could. And if you don't let it expand into steam, that's just going to be really, really, really hot liquid. So it's under pressure, super pressurized. You got to know that. It's pressurized in the primary cycle. That should be underlined. I forgot. Sorry. This is all inside of a containment structure. You can see that. I cut off the term. That should say containment. So that's like the two boob-shaped things that you see on the freeway when you're going to San Diego. You know, those are containment structures. All nuclear power plants have like big igloo shapes or big like aluminum can shapes made of concrete, reinforced with steel to contain the radioactivity. So it's contained. That's called a containment structure. And I need to explain what these do. Those control rods absorb neutrons. They block the sparks. So you've got the reaction started. It wants to keep giving off neutrons. When you add the control rods, they will absorb neutrons before they spark more reactions. So if you're getting too many reactions, you slow it down by blocking some sparks. If you want to speed things up, you can remove the control rods, and now more of the sparks will find uranium-235. So control rods solve the other problem. These are the neutron absorbing material that will keep the sparks from lighting off more reactions. So we can take away the heat and we can control the chain reaction all here. Too many reactions, you've got control rods. Too much heat, you just move the coolant faster. And what could possibly go wrong, right? Tomorrow we're going to blow that. Tomorrow we're going to break reactors. It happens all the time. So we have some famous examples to show you. But first we got to finish with the reactor. The secondary cycle is the generator or the steam cycle. This is usually pretty simple now. That water, sometimes it's special water. Usually it's just plain old tap water. That water comes in cold, touches that pressurized primary cycle. So that pipe was at like 800 or 900 degrees. So that water that came in cold goes and steams really fast. That steam is allowed to exit over the turbine, so it goes wee, and it makes a whole bunch of electricity for the grid. And then that steam condenses on cold pipes from the next cycle. Remember that this is not radioactive. Usually we keep this isolated just in case. But everything about the steam and the turbine and the generator, that's like every other power plant. So all of this could be built by the coal industry. This is not special. And then the third cycle, oh no, I put the wrong picture. Oh man. The third cycle is this stuff right here. I'm sorry, I put the wrong picture. I'll fix that by the time you get back to class. The third cycle is the cold water coming in from the environment that leaves heated. Okay, so please ignore this picture. That's the wrong picture, but that's called the cooling or condenser cycle. That's water from the environment to cool the steam room, to cool the sauna. You can imagine if you have a sauna that's really, really hot and it keeps being heated, then you're going to have to bring in a lot of aluminum cans of cold soda, right? So whether you get this from the ocean or the river or from the municipal supply of your city, it's got to be really cold and you got to have a lot to dump all the heat. Nothing's radioactive. You can put kids on tour in the steam room here. If you've ever surfed San Onofre, you know that there's like a blob of hot water that's coming out of the power plant. That's just ocean water. That's not radioactive. As long as you can dump the heat, everybody's happy. So again, primary cycle, radioactive. Secondary cycle, just steam stuff. And tertiary cycle, I'm sorry I messed up the picture. Tertiary cycle is coolant from the environment that takes away the heat. So you've got heat being made and you dump it and then you dump it. It goes from like 800 to like a couple hundred degrees steam to like, 80 degrees. So you need a whole bunch of water to cool off a little bit of water to cool off a teeny bit of coolant. As long as you can dump this heat, then this cold water can dump that heat, right? I'd like you to imagine as a prelude to tomorrow, what happens if this doesn't work, right? If you can't bring in cold water, right, then this heat doesn't cool down, it goes back hot. And if you have too much heat, you remember what happens, right? We'll do that tomorrow. So let's look at a couple power plants. These are the containment structures. These are like the steam generator part. You can see a whole bunch of power lines that go out onto the grid. And then you bring in cold water from the environment, use that to dump heat. There goes the heat lost to the environment. This is really low quality. That's not very useful. This is the right quality for making electricity. This is your starting super high quality energy. Okay, so primary, secondary, the right level of energy to make steam, and tertiary. This is basically disposal of energy now. So you're taking super energy to make steam energy to make later energy. And here's the ocean version. This is San Onofre down by San Diego. These are the two containment structures. So there's a reactor core in each of them. Here's all the generation stuff. There's more generation stuff hidden back there. You can see the power lines that go out to the grid. And we don't need cooling towers here because we just bring in cold water from the ocean, use that to cool down the steam generators, and then you send that out as warm water. That's a nice place to surf. I hope you have questions, but we did it. We're done. You've done why uranium is special, how to enrich it into fuel, how to stack that into a reactor core, the chemistry that's going to happen in there, why that makes super radioactive waste, and you've explained how electricity is made using the heat of fission. That's a long way to go. It would be totally normal for every student to have a lot of questions. So I'm going to make as much time as you need to answer all your questions, and I hope you have some.